So today we continue with minimum spanning tree algorithms. So one of the algorithms I already told you is called Prim's algorithm. We have already seen a general framework for minimum spanning tree algorithm. In the last class we showed if we maintain this particular invariant, that is, suppose A is a set of edges which you know is a subset of a minimum spanning tree, and you include every time a new edge, and you know that new edge union with the already included edges, that is A, is also a subset of the minimum spanning tree, then your algorithm is correct. And that particular new edge was called the safe edge for A. And that general framework also showed how to choose this safe edge, one of the method. So what was it? First you determine a cut that respects A. What does it mean? A cut is a partition of the vertices of the graph, and it respects the edge set A, means there is no edge in A which has an endpoint on two parts of the partition. So no edge, that means no edge of A crosses the cut. Suppose you have found a cut, such a cut, then you choose that edge which has the minimum weight, and we proved that that edge will be safe for A. So this is what we saw in the most general abstract setting of the minimum spanning tree algorithms. So today we will go over on one algorithm which is called the Prim's algorithm, and we will see how actually this algorithm abiding by that general principle. So let me first tell you what is the general method for this Prim's algorithm. Prim's algorithm, it starts with a single node. Then it goes on building the tree, minimum spanning tree. It chooses one more, it chooses one more, it chooses another, it chooses another. But every time you know this tree is a subtree of a minimum spanning tree, that is guaranteed. So when you have included all the vertices of the graph, at that moment you know it's a spanning tree of the graph, and since you maintain the invariant, it must be the minimum spanning tree of the algorithm, of the given graph. Now for this algorithm I will be using one data structure which is called the priority queue. We already know what is a priority queue and how to implement it. So suppose we can use a heap to implement the priority queue, and I will be denoting that priority queue as PQ. It's just the data structure. We know inserting, deleting, this takes how much time from priority queue? It is order of log n all the time. So now, and I will be using the same data structure for the graph. Remember all the fields, and I will be introducing one more field for each vertex. So this time Vi, there will be one more field called P, which is the priority for that vertex. It will be clear what is that priority will be. Okay. So let's start now. Suppose we start building the minimum spanning tree at an arbitrary vertex whose number is k. So we start MST at arbitrary vertex. You can choose any vertex basically, k. So now with this assumption, the initialization of the data structure is something like this. So initially priority queue is empty, there is nothing in it. Then we initialize the priority field for all the vertices 1 to n. Do if, remember, k is the vertex from where we want to start the building the MST. So if I is not equal to k, then you put the priority of that vertex, a very large priority, some infinity. Else, put that priority as 0. So basically this step guarantees that you get 0 priority only for k, and every other vertex has a priority infinity. And this vi dot pi is equal to nil. So this is the else part basically. I'll tell you what is that pi field will be. Actually, we have already seen what is that pi field. Pi field will tell you from which vertex this particular vertex is being chosen. So basically pi field, through pi field you can reconstruct the minimum spanning tree, just like the depth first search. So this is end if k, sorry, I is not equal to k, then you do all this. Then you put the priority as infinity, otherwise you do this. After you initialize the priority field, you initialize the priority queue. Add I with priority vi dot p to pq, and that is the initialization. So there is, this is a very simple initialization. First you initialize the priority fields of the vertices. We'll see what are those priority fields. Actually you will observe that these priority fields will tell you which edge to choose next. Okay, and with those priorities you just add them up into a priority queue. Okay, now let me write the algorithm. The main part of the algorithm I am going to write. While priority queue is not empty, let me first write the algorithm, then I will explain. I is equal to extract mean. Remember this operation. Extract mean from priority queue. T is equal to vi dot adj while t not equal to nil, do j is equal to t dot v if j belongs to priority queue and wij is less than vj dot p, then vj dot p is equal to wij. I'll explain all this. Vj dot pi is equal to I, and if t is equal to t dot next and while and while. That's it. That is the algorithm. Such a simple code. Only few lines of code. If you have an implementation of a priority queue, you can implement this MST algorithm within an hour probably. Okay, so let me now explain what it is doing. So we already have with the vertices priority and they are stored in a priority queue. So what you are doing, you are extracting the minimum from this priority queue. So initially what will be extracted? The k, because that is the only one with the priority 0, and that is why we put the priority as infinity for all the other vertices. So first it will take the vertex k, and in a generic step it will get the one with the minimum priority. Let's see, suppose it has extracted that, then what it is trying to do, it is trying to see what are the adjacent vertices does it have. So T is equal to Vi dot Atj. Then it's going to it the list of its neighbor. This is this while loop. This while loop is taking care of going through the neighbors of I. And while going through the neighbors of I, what it is trying to see that if, so suppose I have chosen I, this is the minimum already. So when you extract the mean, you will see that this I will be included in the tree. Suppose you have built up to this tree and it has included this I now. When you extract the minimum, it means this vertex now with this edge will be included in the minimum spanning tree. Now what it is trying to do, this while loop, it is trying to see all its neighbor now. So these are not yet in the minimum spanning tree. So these are the say A, B, C, D. Previously they had already some priority, we don't know. But now it is checking whether, suppose this is the J, whether this edge has a weight which is less than the priority it has already got. So initially this had priority infinity. The first time something will be included here, this edge weight will be less than the infinity and this will get that priority. But later on some other vertex may have another edge and this edge may be less than this edge. Then this priority will be reset again. So every time you are choosing a vertex in the minimum spanning tree, what you are doing, you are checking all its neighbor, and if any of the neighbors or all those neighbors which has an edge weight connected to that vertex less than its priority, then you reset its priority. That's what this loop is doing. Why are we doing this? You remember in the Prim's algorithm, what we will do is this: we will grow the tree slowly. So suppose we have grown this tree up to this much, then we need, so this is our H set A in the general abstract setting. So what is the partition? You take these vertices, all these vertices, and the rest of the vertices. This is the graph, rest of the graph. This is G minus A. So these are the vertices, which are the rest of the vertices which will be included one after the other. So now this cart, this part and this part, this forms a cart of the graph which respects A. Now according to that general abstract setting, we can choose the minimum weight. So suppose some of the vertices will have some edges among this. So among these edges, if we can choose the edge which is the minimum, we know we are safe according to our general setting, the abstract setting. And that's what the algorithm is precisely doing. It's maintaining that. When you include this vertex, say, it's trying to update all the other vertices it can reach their priority. If any of the edge has a lower, can give a lower priority to that vertex through this vertex, then that priority is set. So what does it mean? It means every vertex here will have a value equal to the edge which is the minimum among all such edges which can reach this vertex which crosses the cut. Right? So let me repeat this part, what we are doing. So we have this set which are not yet included in the minimum spanning tree. I am claiming these vertices priority will be equal to the edge weight which gives the minimum weight that crosses the cut. because we are keeping that invariant all the time. That while loop is keeping that invariant all the time. And we are happy with that, because if we know that is the minimum, then from the priority queue, if we choose the one which has the least priority, what does it mean? It means you have chosen the edge which is the least weight among those ones which crosses this cut. And we already know our general setting allows this, right? So that's what this part of the algorithm is doing. You can check now. While t not nil is going over the loop of this adjacency list of the neighbor of I, then it's taking one neighbor j which is equal to t dot v. It's checking whether j already belongs to priority queue. See, its neighbor might have been already taken into the minimum spanning tree. Then you should not do anything to it. First of all, it should belong to the priority queue. That means it has not been taken into the minimum spanning tree already. That's why this check, and it's checking now whether this edge weight has less than the already priority value of j. If it is, then you set it. You take the minimum. And again, the pi field you are setting it here. So at this point, you know j will, if j is chosen next, suppose, then j will be reached in the minimum spanning tree from I, and that's what this pi field is doing. Yes.
Then in the initialization, when we put add I with priority vi dot p to pq, we put only the value k or all the.
No, you have to put all the vertices in the priority queue. All the vertices have priority infinity except the vertex k, which has priority 0. Every other vertex has initially the priority infinity. So when you do the extract min initially, only the vertex k will come out. And in the as the algorithm proceeds, all the other priorities will be set. We'll take an example. If it confuses you, we'll take an example, we'll see how the priorities are getting set, and then it will be clear to you. Okay, so that's what it is doing, and here t is equal to t dot next. So this is the algorithm. So let me just take an example now to make clear that what exactly how the algorithm is working. So let me take a graph. We'll take a little bit complicated graph, not a very trivial graph we will not take, so that we know what is happening. So I'm just drawing one graph, some arbitrary graph with some edge weights. So I'm putting the edge weights here. These are the edge weights. 1.4, 1.3, 1.4, 1.2, 1.5, 0.9, 1.6, 2.5, 1.6. Okay, and now I am numbering these vertices. So these are the numbers for the vertices. This is 1, this is 2. So let me number with a different color so that we are not confused. Say this is 1 with red, 2, 3, 4, 5, 6, 7, 8, 9. Have we numbered everything? Yes, we have numbered everything. So there are total 9 vertices, and this is the graph, suppose. Now let us see how the algorithm will proceed. What I am going to do, here I am going to write the priorities of the vertices 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 vertices. So initially, suppose we start our MST growth from say vertex 1. So initially 1 has priority 0, 2 has priority infinity, 3 infinity, 4 infinity, 5 infinity, all are infinity. So initially these are the priority values for all the vertices, except 1 is 0. So what will be extracted at this stage? So extracted will be remove 1, right? So 1 will be extracted. When you extract 1, who are the ones which will be updated? 2, 3 and 9. In the while loop, you will see, because these are the neighbors of 1, and so this will be extracted. To 2 has an priority now infinity, but now you will check I and j whose age weight is 1.3, and 1.3 is less than infinity. So its priority will get 1.3. 3 will be 1.2, because 1.2 will be less than infinity. 4 will remain as it is, 5 will remain as it is, 6 will remain as it is, 7, 8 and 9 will now change to 1.6. So now we just look at what is the MST has done, that algorithm. It has chosen the vertex 1, and from this set, what is the partition now? 1 and rest of the vertices. And what are the edges which crosses this partition or crosses this cut? There are only 3 edges which crosses this cut, and these 3 edges are nothing but this, this and this. And you see, you have updated accordingly the vertex 2, 3 and 9. So according to our general setting, what should you choose? So there are 3 edges which are which crosses the cut. According to these 3, you should choose the next one is the minimum one, and 3 will be chosen. So next step we will remove 3. So when you remove 3, let us look at it. You have removed 3, its neighbor have to be changed now. Its neighbor is 2, 1, 8 and 4. So for 2, what is the age between 3 and 2? Its age weight is 1.1, and 1.1 is less than 1.3. So priority of 2 should be changed to 1.1. So this you should look at this now. So previously the cut was, this edge was crossing the cut. Now also when you include 3, this edge will also cross the cut, but you are as if retaining this edge over this edge, because this will be minimum over this edge, and in any way we are going to choose the minimum, so we should not keep this edge. And that's what this while loop is doing. So now this will be updated to 1.1. What about 2, 3 is not, we have already removed it. Then 4 will be updated to 1.9. 5 does not get affected. 6 does not get affected. 7 does not get affected. 8 gets affected. Now 8 has 1.4. and 9 does not get affected, remains 1.6. So in the minimum spanning tree, now you check what is happening. You have taken 1, you have taken now 1. You have taken also 3, and this you have taken with 1.2 age weight. So this is the minimum spanning tree now. This. So you have taken 3 and taken the vertex 1. And what is the cut now? There are 2 edges here. So there are some other edges going. So these edges now are in the crossing the cut. So now let's see, from 1 you could have reached 2, from 3 also there is a age which you can reach 2. Among these ages you are keeping the minimum. That's what this update. There was 1.3, this is 1.1. You are between these two, you are as if keeping this. So this is the setting the priority of 2. So if at all 2 is chosen next, you know it will not be chosen through this edge. It has to be chosen through this. So that's what the algorithm is doing in the while loop. Algorithm is very efficiently written. You are doing all the edges and everything using a priority value of the vertices. You are setting the priority of the vertices. It's a very nice algorithm the way it has been written. You could have written it differently, but it's very compact and very nice. Okay, so this is the algorithm. So let me now complete. So probably you have understood now the procedure. So let me just complete. Remove 3. So next, which one will be removed? So remove 2. So 2 will be removed, and when you remove 2, we will check first for 3. 1, 2, 3 has been removed. So for 4, 2.8. You see from 2 to 4 there is an age from 2 to 8, 2.8. But 2.8 is not less than 1.9. So this will not be updated. It will remain 1.9. 4 remains. 5 is affected? No. 6 is affected? No. 7 is not affected. 8 is not affected. And 9 is not, sorry. This remains 1.4. You cannot change. So this remains 1.4. This remains 1.6. Sorry. Okay. And you see why we have to check whether 1 is already in the priority queue. Otherwise, you would have set again the priority of 1 as 1.3 to 2. Since you are checking whether, because 1 is not in the priority queue anymore. So you will not set the priority of 1 through 2 anymore. That's why we did not take care of it. We did not write anything here. That check is needed. Unnecessarily you will be setting otherwise the priority, and probably the algorithm will choose the wrong one next. So next time which will be removed? 8. So remove now 8. So when you choose 8, 1, 2, 3 has been removed already. 4 does not get affected, so it remains 1.9. 5 gets affected now. It gets 1.3. 6 gets 1.4. 7 remains infinity. 8 is removed now, and 9 is, does it get affected? Yes, 2.5, but it has already 1.6. So it 1.6 retains. So next time which will be removed? 5. So remove 5. 1, 2, 3 has been removed. If you choose 5, does 4 get affected? 3.6, but 3.6 is not less than 1.9. So 1.9 retains. 5 is removed. 6 gets 1.2. 1.2 is less than 1.4. So this will be 1.2. What about 7? 7 gets 1.5. 8 has been removed. 9, 1.6. So next time so you can continue now. I don't have to go over this entire thing now. So yes. So you choose anyone. Choose anyone. It doesn't matter. If yes, that's a good question. If 2 vertices have same priority, which one will you choose? You choose anyone. The general setting, if you go back, you can see that choosing anyone is fine. It does not affect the invariant. Yes.
It's not possible that if we start with a different node, we might end up with even more minimal tree.
How can you do that? What is the definition of a minimum tree?
So
What is the definition of a minimum spanning tree? So his question is, if we start with another vertex, do we reach a better minimum spanning tree? But this question itself is wrong. Why? I tell you, there is nothing like better minimum spanning tree. What is the definition of a minimum spanning tree? That it is the minimum among all the spanning trees. So you cannot have you can have 2 different minimum spanning trees. That is fine. But you cannot have 2 minimum spanning trees with different weights. No.
What is the proof that this gives the minimum spanning tree?
That is the proof I have already given. In the general setting, that is the proof why it gives the minimum spanning tree. In the general setting, what do you have to keep? keep the invariant, you have chosen the edge set A, you take the cart which respects A, and you take all the edges which crosses this cart, take the one which is the minimum among all those edges, and we are exactly doing this.
The first step, nothing is mentioned about how to choose the first edge. I mean, the first node.
You can choose any node, it doesn't matter.
That's what I don't know why it doesn't.
Why? Because what is your A now? A is empty. You have not chosen anything, and you know the first node you have chosen always belongs to the minimum spanning tree, which is fine, right? Any node has to belong to the minimum spanning tree. So you have chosen the first node. Your A is empty. Your cart is respects the cart. Your cart is basically all the edges which are going out of that particular node, which respects the cart, the edge A, which is empty basically. Then you take the minimum, which is the algorithm is doing. So this is the, so you have to understand why this algorithm is working because of that proof. And now you tell me, how much time does this take, this algorithm? How much time does this algorithm take? First let us see. Do not say n square. Where from n square is coming? I do not see n square is coming here. Let us see, go step by step, rather than throwing random values n square, n log n. First of all, initialization takes how much time? You remember there was a initialization step. How much time does this take? So let me put that slide here. Yes. Is it order of V or order of V log V? It depends how you build the tree. If you build the tree, there are two ways to build the tree. You can take one vertex at a time and put it incrementally, or you can take all the vertices together and build the tree bottom up. If you do the next one, the second one, it is order V, otherwise it will be V log V. So initialization is not more than V log V. Alright. Now let us see this while loop. How many times, what is the complexity of this step? Extract mean. This is the minimum extraction from a heap. Order log n, and how many times you will be doing it? E times? D times. Yes. So how long you will do? While PQ not empty, how many vertices the priority queue has? V vertices. So every vertex will have extract mean. So total, so this will be V log V totally, or I am just expressing it as n log n. N is the number of vertices, m is the number of edges, suppose. So this is n log n. Now let us see this while end while. This thing is going over the neighbor. This the total will be E, right? Total will be E because this is the summation of the list of the neighbors. So which we know already E, but is it constant? Within the while loop, which one will take some time? Which step here will take some non-trivial time? It's not constant. J element of PQ can be done very efficiently. What you can do, you can maintain a mark field. You can maintain a mark field in the VJ. So when you extract the mean, you basically set that flag off. Check that flag whether that flag is off or on. So that can be done in constant time. So this is not the one which is time consuming. The time consuming step is here, which I have not written a little bit. So when you are setting a new priority, what do you have to do in the priority queue? You are setting a new priority. You have to rearrange it, because otherwise probably it might have changed your priority queue, because its priority has changed. It has to be replaced somewhere. It has to be placed in its proper place. How much time does that take? Log V or log n. Here what I have not written is this step. VJP is equal to Wij, then update PQ. That update step I have not written it here, but that update will take log n time. So this is the time consuming step. So if you do log n per edge, what is the total time this will take? Or m log n. So this will be total m log n, right? So what is the total time do we have? So total time of this algorithm is how much? M plus n log n, right? Now here comes the data structuring part. Can somebody tell me how can we improve without doing anything? This algorithm remains same. Only thing we will use a little bit clever data structure, and suddenly we will get an improvement in the time complexity. We already know something about it. Yes, very good. So what we do, instead of using a heap as a priority queue, we just use a Fibonacci heap as a priority queue. Remember, in a Fibonacci heap, extract mean, how much time does it take overall? If you do n extract mean, it takes, no, it's not constant. N extract mean will take n log n. N extract mean will take n log n. It will take n log n. You go back. That is the amortized time. Extract mean is log n and total will be n log n. Okay. Now what about this one? This step is nothing but what? In a Fibonacci heap, decrease key. And how many decrease key you are doing now? M decrease key operations are there here. And what was the amortized time for decrease key in Fibonacci heap? Order 1. So M decrease key will take how much time? Order M. So total time becomes now how much? So with Fibonacci heap now, so with Fib heap, the complexity becomes how much? M plus n log n. And definitely this is better than this complexity. Why? Why this complexity is better than this complexity? Because of the log n factor. This log n factor, here also there is a log n factor. Yes, here there is a log n factor with m, and m in the worst case can be n square. Then this worst case become n square log n, but now it remains n square here. And see, we didn't change anything, we just used a better data structure. And now you should appreciate what is the power of amortized complexity. See, each one in each decrease key here probably will take a very worst case time, a long, not constant time. If you look at the decrease key operation in Fibonacci heap, the worst case time of decrease key is not order 1. It can be in the worst case probably order of n or order of log n. But we know amortize is order 1. If you have total m operations, that cannot be more than order n. That is the main thing here. We are doing m decrease key, we are sure that m decrease key will not have more than order m. Though one of the decrease key can be very bad, but it will be compensated by the others. So that is the power of data structuring here. So you are getting a better algorithm using a better data structure. And also we will see in the next class that this algorithm, the way it has been written, why am I saying is very efficient or why it is very nice? You will see we will have a totally different problem, which is called the shortest path computation in a graph, which is not related to minimum spanning tree at all. But with a minimal change to this algorithm, only 2-3 steps I will change and you will get a solution for that problem. If some of you know what is Dijkstra's algorithm, Dijkstra computes the shortest path from its source. There also it uses the priority. If you remember, it sets the priority to the vertices. So we can use the same algorithm, same technique, but only thing is we have to change how to update the priority. That's it, and you will get a solution to a totally different problem. Okay, so we finish here today. You will see in the next class the shortest path tree. Then I will go to the other algorithm of Kruskal. I told you there are two algorithms for minimum spanning tree. This is one algorithm which is called the Prim's algorithm. There is another algorithm called Kruskal's minimum spanning tree algorithm. We will take it up after that one.